Okay, yeah, so I don't think I don't know what's wrong with my camera today, but it's not coming on today. So sorry about that, but that's okay. We'll just proceed without. Okay, so welcome everybody. How's everybody doing?
Good.
Good. Okay. Any questions on anything before we get started? Who remembers what we were talking about last time?
Neural networks.
Neural networks, awesome. Okay, and so we got almost to the end of what we were looking at yesterday. I was going to go back and do that one last example, go through that one last example, and then we'll move on to talking a little bit about TensorFlow. But yes, we started learning about neural networks, and I'll do a little recap of that in a second. Actually, let me do my recap first. I think this is going to go better. Okay, I'm going to do a little recap, then I'm going to go back and do that last example using the MLP regressor function that we didn't get to last time. And then we're going to talk a little bit about doing neural networks in TensorFlow. So a few recommended readings here. Also, I noticed that this link was broken in the version that I posted. Sorry about that. Now this is working, but maybe you just want to Google that one to find that resource. Sorry about the broken link, but a couple of resources that will be handy for today's content. Okay, and so let's just do a little recap of what we were talking about last time. We got introduced to neural networks and learned that they can be used for both for classification and regression. Lots of different architectures out there, so this can be quite a big area, lots of different topics. We focused on kind of the simplest setup, which is the multi-layer perceptron. And so in this case, what we have is we have an input layer. So think about, each of these little red cells is representing a feature or one of the dimensions of our data, right? So if we had 8x8 pixel images, we'd have like 64 of these guys. And then we feed this in, and then there's like several hidden layers inside the network. In this picture, you only see one. Normally, there's more than one. When we're doing neural networks, there's typically more than one hidden layer. We usually have a series of these hidden layers. And then finally, we have an output layer. And now the dimensions of this output layer will need to match whatever your problem is. If you're doing regression on a univariate function, this would be just like one-dimensional output. If you're doing classification with K classes, you're going to have a K-dimensional output, a node for each class. Okay, so given a set of features or an input, let me call this input x0. So this is my initial data going into the network. And let's say it consists of n features, x1, x2 through xn. This notation might be a little bit confusing, but right, this x0 is a vector, and then each of these x's is an individual entry. And associated with this input, I have a target y, a value of my response variable. And then the neural network is going to work as follows. So in each layer, I'm going to apply an affine transformation. I'm not sure we used that term exactly last time, but that just means this part right here. When we say, I know like when we're doing pre-calculus, when we say linear, we mean like mx plus b, we're including that intercept. But normally in the context of like linear algebra and other things, by a linear function, we would just mean this first part, the w times x. And if we want to include the, plus b part, then we call that an affine function. Okay, so it's just this generalization of linear functions that includes this little intercept here. So we do an affine function, wx plus b, and then we feed that into an activation function, which could be ReLU, hyperbolic tangent, or logistic, et cetera. And we're going to iterate this. So this is the idea of a neural network. So if I input, x0, I do some affine function of x0, apply my nonlinear activation function, and I get x1. And then I can iterate in this way. If I feed an xj minus 1, compute affine function, take the nonlinearity, and then I get xj, and I just keep doing this through the network. So at the jth hidden layer, the input is represented as the composition of j of these mappings. Okay, and an addition, for classification problems, an additional function called a softmax function is generally applied to the output layer. Okay, and we're going to go into a few more details on that and look at an example to kind of help that click. Okay, and then just remember, so here, y hat, we're referring to the prediction made by the neural network. And we want these y hats predicted by the neural network to match up with the y's in our training data. Here's some pictures of different activation functions that you can use. The most popular is ReLU, this one here in pink, which is just 0. And then it becomes the line y equals x over here. Some other options are the logistic function shown in green, hyperbolic tangent shown in blue. And here you can see the derivatives of all of those functions. Anyone remember why ReLU was popular over some of these other options from this derivative plot? What was nice about that? Anybody remember? Oh, I got a response. No vanishing gradient. Excellent. Thank you. So yes, you notice on this blue and green, the derivative, it decays to 0. And so you're seeing like a vanishing gradient, right? As the values get large, the gradient disappears. This is referred to as derivative saturation, but ReLU has a nice stable derivative, which just stays at 1. So that's a nice property for training a neural network. Okay, so let's look a little bit at the softmax here. Well, the softmax function, so in general, if you do this neural network, you have input, you have your hidden layers, and then you have some output. There's no reason that output is going to be in between 0 and 1. Like there's no reason that was going to output a probability. It's just going to output some score, but not necessarily a probability. For classification problems, we really want it to output a probability so we can say what class something belongs to. So let's suppose we're doing a classification problem with k classes. Then the softmax function, so we're going to have our output is going to then be k-dimensional. And we can define the softmax function by the jth coordinate of the softmax of the vector z. Well, let's take the jth coordinate of z and we'll exponentiate it. And then we'll divide by the sum of all of the other entries exponentiated, of all of the entries exponentiated. Okay, so what this does is no matter what the range of z is, it's going to map the vector z to a vector of numbers, all of which are in the interval 0, 1, and so that all of the values sum to 1. So it will really think of this as a probability distribution. So we interpret the jth coordinate of the softmax of z as the probability that z is in member class j. Okay, so for example, let's say I'm using a neural network and I want to distinguish cats from dogs from fish. Okay, so if these are my only classes, my output layer is going to be three-dimensional. Let's say the first one corresponds to cats, dogs, and fish. And let's say my neural network outputs 20, 10, 6. Okay, so the highest entry corresponds to the cats for sure. And so if we're thinking of these as, like scores, highest entry is the most likely one, then if I just think about looking at where the maximum occurs, well, the maximum occurs here in the cat's entry. So I could put a 1 there and zeros everywhere else and basically interpret that as I'm predicting that I'm a cat and I'm not a dog or a fish. So the softmax is actually quite similar, but if you apply the softmax function to this vector, what you actually get out is, 0.999999953 and then 0.000004. So you get something very similar to if you just took the maximum, it's very similar to this 1, 0, 0, but the nice thing about this function is it's smooth, so you can take derivatives. That's not true just of the maximum, and we can still interpret this as a probability. Okay, so think of this as similar to taking a maximum to decide what category you're in, but it's like a smoothed version where you're getting a probability distribution across the categories. Okay, any questions on the softmax? Okay. And so then we also talked a little bit about training a neural network. So remember, when we're training a neural network, we're trying to figure out what are the best weights to use. Back up here, we see at each iteration, at each layer of the network, we have these parameters W and B. Sometimes we just, call all of those things W. So those are all of the weights. So here by my W, I mean the WJs and the BJs that are occurring in every single layer, right? So I have maybe, 10 matrices and 10 biases. And we're trying to find the best values for those things, the best values of all of those weights. And those are the ones that are going to minimize this loss function. And this loss function consists of two parts. First, we just have a data fit part. We want to choose weights W, which give us Y hats, which match up really closely with our Ys, right? We want Y hat to be close to Y. So we want this to be small. This is our data fit term. And then the second term is a regularization term that you throw in there to prevent your neural network from scaling up the weights really, really large, because you can get some unstable behavior that way where you get like really good accuracy on the training data, but you're making your weights like super large to do it. So this regularizes things a bit and should make the models more generalizable. Okay. So, and this for the data fit part, this G, if you're doing a classification problem, usually that's chosen to be cross entropy. And if you're doing regression, a lot of times it would just be like the L2 difference. Okay. And so we want to minimize this thing. We want to find the W's that give us the smallest value of loss. How we actually do that is through various optimization methods, most of which are based on some kind of notion of gradient descent. Most are some kind of gradient descent, like stochastic gradient descent or atom or quasi-Newton method. And so for most of these, you have to compute a gradient of your loss function, the gradient with respect to W, right? As you change W, how does your loss change? And to do that, you don't need really any fancy math. Mainly, you just need to know the architecture of your network and you need to know the chain rule, but there's a clever way of organizing these calculations to compute these things quickly, because if you have a lot of layers, it can get really messy. And that kind of clever way of organizing the calculation to compute the gradient is called backpropagation. Okay. And then, so we sort of distinguish these two setups where we're doing, one where we're doing regression, one where we're doing classification. And last class period, I think all of our examples we did were on classification. We looked at the multi-layer perceptron classifier. So let's go back and do this last example. Now that we've had, I thought it might be helpful to do our recap first. Now let's go back and do this last example, which is using the MLP regressor function. So remember, these were in scikit-learn. And I probably need to run my imports again. So let me maybe scroll up here and make sure I'm good to go. Okay, hopefully that was everything I needed. Okay, so this data set we're going to be looking at is sorry, too much scrolling. Okay, so this data set is a California housing data set. And so we'll use that MLP regressor function. So first of all, I can just load the data. Take a look at what the keys are. So here, what do I have stored in this data set? I have the data, the target, frame, target name, features name, description. So the description, it would be helpful to print. So we can look here at the shape. This data set consists of about 20,000 data points with about 8 features each. And here there are data set characteristics. Right, so 20,000 data points, 8 features. The features here are median income, house age, average number of rooms, average number of bedrooms. So these are all related to like what you might expect the price of a home to be in a certain geographic unit. And that is the target variable. So the target variable is the median house value in a certain geographic unit. I'm not exactly sure what the geographic units are, if they're like, how granular they are, but in each geographic unit, you're looking at these features. And then this is the variable, the median house value is the variable that you want to predict. Okay. All right, so let's take a look. First of all, we've done similar problems to that when we just did linear regression. I think we had like a very similar type of data set. So we can do that too. We can just do regular linear regression. We split this, oh, sorry, I forgot to say that, but when we used our train test split to split the data into training and testing. So now that we've done that, we can, fit a linear model on the training data, and then we can evaluate it on the test data. That's what we're doing here. Now this is using all the variables, right? So you might say, well, maybe you're overfitting, and possible, right? That's possible. But what we get here is an overall score of 0.62, okay, where 1 is supposed to be good. So that's not great. On the other hand, if we try this, we can try this with neural networks. So we call our MLP regressor function from scikit-learn. We can specify our hidden layer sizes. So we're going to have 2 hidden layers, each with 8 neurons. And we're going to use Atom for our optimization. And then we can take a look at how, again, we're going to fit it to the training data, and then we're going to evaluate it on the test data and see what we get. And I got a little convergence warning here. Stochastic optimizer maximum iterations reached, and the optimization hasn't converged yet, right? So we can always, so any suggestions of what we might do in that case? We got a little warning here that it didn't converge.
Increase iterations.
Yeah, we can increase iterations. Let me see if I remember the syntax for it. I don't know if I do, but let's try it. Okay, I think I did. Right, so default was 200, increased it to 500, and it didn't yell at us, so that was good. So I think it will warn you if it doesn't converge. So now it looks like it's converging, and we're getting a score of 0.7767. So that is a good bit. I mean, it's, could be better, but it's a lot better than we were getting with the linear regression. Okay. So yeah, really, this works in a very similar way to what we were talking about last time. It's just for regression. Yeah.
So does 0.77 basically represent like a correlation?
I think so. I think that this is like a correlation score here, but I'd have to double check the documentation to be 100% sure. Yeah. Good question, and I should have looked that up. I can check that at our break. Let's see. Oh, and I didn't see the chat. Thank you, everybody. Increase iterations. Excellent. That's what we did. Up alpha or increase iterations. So that would be something we could try. We didn't try that, but increasing the iterations worked. Or would it be tall? So, I mean, one thing that affects this is the learning rate. That's one of the things we were talking about last time, where increasing your learning rate can be a little dangerous because you start taking big steps. But if you're not converging, maybe you need to take a few bigger steps than what you're taking. So we could have tried that. Let's see. Learning, what is the current learning rate? The learning rate is constant, and the learning rate initialization is 0.001. So if I take this out and I try increasing my learning rate, that might also fix it. I'm not 100% sure, but let's increase it and see if it converges without. Yeah, so that worked too, with the default number of iterations. By choosing a larger learning rate, we're taking bigger steps. And so that got us where we needed to go in this case, apparently without any bad side effects. Okay, and definitely the tolerance could, I mean, if the tolerance is set just like way too crazy low, then it may say you're never converging when you actually are. But I don't think that's what was happening here. Okay, so so if you're interested in neural networks, here's some nice little videos. There's 7 of these. These are called Neural Networks Demystified from Welch Labs, and they're a good place to start. There's code on GitHub that you can get for that. And then, so we've been looking at neural networks in scikit-learn. However, as we've noted, this implementation does not really scale to large scale applications because there's no GPU support, and you have a little bit less flexibility in designing the architectures that you want to implement. So they're more limited architectures, but there's lots of other options out there if you want to do large scale applications, and if you want to, really have more control over your architecture, here's just a list of some different packages that are out there. What we are going to be talking about today is this first one on the list, which is TensorFlow. So this is an open source C++ software library for numerical computation. And it's implemented in Python. You can run it in Python, and it works very well in Python. Okay, so let's do that. Welcome back to today's lecture. So let's talk a little bit. All right, so these were the limitations of the scikit-learn implementation. And so let's take a look at an alternative way that we could actually tackle those same data sets that we were looking at, same setup, but using TensorFlow. So if you don't have TensorFlow, and you probably don't unless you have installed it previously, you'll need to install it. So you can just do pip install TensorFlow before running this workbook. And then you'll need to import it, and you can check your version. So I've got 2.8, which I believe is the latest version. And the idea of TensorFlow, the idea of how it computes things, is basically to create what are called computational graphs. The computational graph, what are we doing? Well, let's just take a look at the picture here for a second. So take a look at this graph. So what do we have? We've got some variables. These are in the squares, right? I've got X, I've got Y, I've got this constant, and I've got variables in these squares. And then I have these operations like multiplication, addition. And then this graph is showing how these things are connected to each other, right? So here I'm going to take X and multiply by X. That's going to be my square. And then here I'm going to take that and times Y. So this graph is defining how to combine these things together in a precise mathematical way. Okay, and so that's kind of what TensorFlow does. I know it's a little vague, but essentially there's two components. There's a construction phase where you build a computational graph. Okay, so you just like specify this structure here, but you don't actually compute anything. And then there's an execution phase where you initialize the variables in your graph and actually evaluate the functions. You actually like flow them through these operations. However, it's now become a bit easier to work with these things in TensorFlow. And TensorFlow 2, they implemented eager execution, where you don't have to like explicitly do this yourself in terms of define the construction and define the execution where it's happening more behind the scenes. But let's just kind of take a look here at how you would do some of these computations in TensorFlow. So for example, I can create TensorFlow variables. So here I'm going to make X and Y. I'm going to make them TensorFlow variables, and I'm going to give them an initialization. So these are still variables, but I'm giving them an initial value, which is here in this parentheses 3, 4. Okay, and then I have some function, which is X squared times Y plus 2. This is the same function up here in the picture. And then I can take that F, and if I print f.numpy, you'll see it actually just returns a number, right? So because of how I initialized the variables, it's actually just computing this. And so another handy feature in TensorFlow is its ability to auto-differentiate. So it can automatically compute the derivative of various functions using something called gradient tape. So here's a little example of a simple function. Let's say I start off and I make X a TensorFlow variable initialized to 3. Then if I want to take the derivative, here's the syntax, which is, maybe a little weird, but here's how it goes. So I would say with tf.gradient tape is tape, then I would define my function, y equals x squared. And then to differentiate it, I can say, okay, my derivative dy dx is tape.gradient of y with respect to x. And then if I call that dot numpy, it tells me 6, right? So why is it 6? What is it doing? It's computing the derivative of x squared. Well, that's 2x, but then it's evaluating it at x equals 3, because that was the initialization we gave the variable. Okay, so this is handy, right? Because it's not doing this like with difference quotients. It's actually knowing how to differentiate things. Okay, here's an example with 2 variables. So let's say I have x and y, 2 TensorFlow variables, and same syntax here, except now I have a function that's defined in terms of 2 variables. And so then I can make my gradient as tape.gradient of f with respect to both x and y, because now I've got a 2-dimensional function. So this is going to give me, an array, 2 entries. And so if I look at the first part, I'll get 1, second part, I'll get 16. Okay, so that's just sort of illustrating how we can define TensorFlow variables, how we can differentiate functions of those TensorFlow variables. Okay, so this is really helpful since when you're training a neural network, you've got to take a lot of derivatives. You're differentiating this loss function like over and over again. So being able to do that quickly is really important. Okay. All right, so let's, now that we've talked a little bit about taking derivatives in TensorFlow, let's talk a little bit about optimization in TensorFlow. So TensorFlow has several built-in optimization methods. And here we're going to be looking specifically at those available in Keras, which is an API that sort of runs on top of TensorFlow. And here are the different options that we would have for the optimization when we do that. We saw a couple of these last time. We saw Atom, we saw stochastic gradient descent. Here we've got a few that we didn't see last time, this ADA delta, ADA grad. Yeah, so you can look through that list. If you want more information, check out the Keras webpage. And let's try it out. So here we're just going to be playing around with a couple of toy examples, and then we'll do some real data. But let me show you the syntax that you would use if you wanted to use TensorFlow to, first of all, define a function, and then secondly, optimize that function with this built-in optimizer in Keras. Okay, so this is probably what you're familiar with from what we've done in class. This is just, how you would define your normal function in Python. So what you're going to do to minimize that function is you're going to define another version of that function, as you see right here, where you don't list the inputs, right? Normally you would list the inputs in here, but we're going to need to define this in the following way, where we don't list the inputs, but other than that, it's the exact same. Okay, so this is just the syntax that's needed for this optimization. Okay, and then we also have this reset function, and what the reset function does is it just defines these x1 and x2 as TensorFlow variables, and also initializes, gives them initial values of 10 and returns them. Okay, so to do this, we need to have the function defined in this slightly alternate way, and then we initialize, and then we we specify the optimization algorithm that we want to use. So here I'm going to use the stochastic gradient descent with a learning rate of 0.1. And then we can just run this. And so what this is doing, so for I in range 50, so we're looping over a set of iterations, and for each one, we're applying opt.minimize of this function. But notice what this is doing. This is just doing one iteration. So like what we did before, we would run the optimization and it would just, do all the iterations until convergence. Here, this opt.minimize is just computing one iteration in the minimization. Okay, and here we can output what's happening here. So Y, this thing we're trying to minimize, it is going down, so that's good. 170, 108, and then it's showing you the, the X1 and the X2 that associated with that. So it looks like it, it's converging, right? So it's converging to a minimum value minus 2.2. Okay. So we can try some different optimizers for that same function. And also, I guess maybe different like initializations. The learning rate is quite important. So, okay, so let's see. So up here, yeah, it's this, yeah, it's just a different function. So let's try this one. Here we've got another function. We've got x1 squared plus 10 times x2 squared. And we're initializing x1 at 3 and x2 at 2. And we're going to use Atom with a learning rate of 0.1. And let's see what happens here. Okay, so it looks like our values are decreasing, which is good. They're getting smaller and smaller. And then it looks like we're converging, right? This is going to 0. And this kind of makes sense. This is a bowl, right? Actually, let me show you the picture here. Here's the picture. So what this function is like a bowl, it kind of looks just like you don't see it come up the other sides, but it does come up the other side. It's just kind of an elongated bowl. So it's kind of like, it goes like this, and then it's kind of wide in this direction. But there's a, unique global maximum there at 0. So you would want it to converge to 0, a minimum loss of 0 at the point 0, 0. And this is exactly what's happening. But let's see what happens. Well, first of all, let's try it with stochastic gradient descent instead of Atom. Let's see. Okay, it didn't go so well. Look at that, right? So when we changed, when Atom it was fine. Now we changed the optimizer to stochastic gradient descent. It decreases like a little bit to 40, and then it just stays there, right? And it looks like the X1 is 0. But what's happening to X2? It's just bouncing 2 minus 2, 2 minus 2, 2 minus 2. It's just bouncing back and forth. And it's never actually going down the bowl, right? It's still staying up. Okay, so any suggestions what to do in this case? You can tell it hasn't converged because this is bouncing around, right? You shouldn't see the X2 bouncing around like that. It should be staying at the same value. So what could we do maybe to get it to converge? Will increasing the number of iterations, oh, I have something in the chat. Adaptive learning rate. Yeah, so we can play with the learning rate. I guess I'm not 100% sure if this one is adaptive or constant, but we can definitely make the learning rate smaller, right? When it's not here, like before, it didn't converge because the learning rate was too small, but now, and we didn't have enough iterations, but now it's not converging because the learning rate is too big and it's like overstepping where it needs to go. So if we make the learning rate smaller, you can see it looks like now we're actually getting some good behavior, nice steady decay all the way down to well, we haven't quite gotten there yet. Actually, looks like now we got stuck at a, let me see if I increase the number of iterations, if this will, let's see if I go to 200. As you can see, sometimes you have to play around with these things. Okay, now I've converged. Okay, so sometimes this is a little bit of an art, right? These are important parameters and they do really affect things. And, you know, sometimes it's too small, sometimes it's too large. Is this called hyperparameter optimization? You would refer to the learning rate as a hyperparameter. Do you mean this sort of like trying to figure out the right way to pick it? Yeah, I don't know that I'd call it. I mean, what we're doing, I don't know that I'd call hyperparameter optimization because I'm just like playing around with it. But perhaps I think there are, you know, whatever, more rigorous things one can do to do hyperparameter optimization. Good question. I'm just doing hyperparameter playing around with. Okay. But yeah, to make that precise, if you really want to talk more precisely about hyperparameter optimization, then you probably have to like define some kind of loss function in terms of your hyperparameter. So you'd need to think about, you know, how to do that. So some kind of loss function and defined in terms of the hyperparameters that you're trying to optimize. Okay, so you can see these things are a little bit sensitive, learning rate's important. And I should say that function is a nice function. It's a convex function with a unique, you know, unique critical point, one global minimum convex function. So that's kind of, well, I guess it's a cautionary tale that even with a function with really nice properties, you know, things can still be a little tricky. Okay, and this was me just plotting the function so you could visualize it. Okay, so let's see. Maybe that's a good point to take our 5-minute break because that's kind of a good stopping point, and then we can come back and we can look at some real, doing this on some real data. Okay, it's 4:24 right now. Let's come back at 4:29. Someone had asked last time, this is not part of class, but this is like a little side note. Someone had asked about what exactly is an epoch. I can put this in the chat. I found this little link on that. But yeah, basically it's like related to the batch size. And in an epoch, you like use every data point once. But you might, it's not the same thing as an iteration. So like depending on your batch size, your batch size will determine how many iterations per epoch you have. Okay. Yep. Okay, why don't we get started again? So let's take a look at the following example, the MNIST example, and see, so we did that example last time, but now let's see how we can also use TensorFlow with Keras to do a neural network for MNIST. So as I was starting to say earlier, Keras is a high-level neural networks API, which is written in Python and capable of running on top of TensorFlow and other packages for neural networks. And we'll use it with TensorFlow. So, so the data is, I guess these are maybe a little bit larger than some of the times that we've looked at the data set. These are 28 by 28 pixel images of 10 classes. And so we're going to make a neural network which has 2 hidden layers. In the first layer, we'll have 300 neurons and 100 neurons in the second hidden layer. And the idea with Keras is that we, like I said, there's a little bit more flexibility here, so we can sequentially build the layers in the neural network. And for each layer, we can specify the type and the size and the activation. So we could do like different activation functions in different layers. And we can also start off with a flattening layer to vectorize the data, since it's given to us as these like patches, 28 by 28 patches. It's a classification problem, so we'll be using cross entropy for our loss. Okay, so to get started, we're just going to import TensorFlow, NumPy, and confusion matrix for evaluation. And MNIST is also one of the data sets available in tf.keras.datasets. So here I'm just going to load this. And, well, sorry. I'm specifying this data set, and then in the next line, I'm actually loading the data. This data comes pre-split into training and test, so that's kind of nice. We don't have to do that explicitly. We can just load it, and we have our training data and our testing data. And then I'm just going to rescale the both the training and the test data. So these are going to, I believe they will. The values are integers, you know, ranging from like 0 to 255, divide by the maximum possible value to put everything on a scale of 0, 1. That's not, you know, necessary, but I'm thinking that's going to have some benefits in terms of numerical stability. So it's maybe a good idea. Okay, so here we actually specify the architecture of the network. So first we're going to specify, you know, we're going to make a model using this tf.keras.models.sequential. And it's going to consist of the following. So we're making a neural network. We're specifying the architecture, and it's going to consist of the following layers. So first layer is just, we're just going to flatten the input. So this is a flattening layer. The data is 28 by 28. We want to just turn it into a long vector of size 784. Okay, the next layer is going to be a dense layer. A dense layer means you've got arrows, you know, going from every neuron in one layer to every neuron in the next layer. And that's what we were talking about last time. That's kind of your basic setup where you're representing this flow as like a matrix. So this is a dense layer with a ReLU activation, and then another dense layer with a ReLU activation. And then finally, we're specifying our last layer, which is our output layer. And remember, we want to make sure it has dimension 10 because we have 10 categories here in the classification. So we can do this and take a look at the model summary. Okay, and this is handy. And also keep tracks of how many parameters we have going on here. So first, we just have a layer that flattens. So the shape here is, you know, like just 1 by 784. And then, right, we feed it into this next layer of dimension 300. And so what do we, how many parameters do we need to do that? Well, we need a matrix that's 784 by 300 plus a 300 dimensional bias. So that's where this number is coming from. Probably a little bit easier to see when we're going from the 300 dimensional layer to the 100 dimensional layer. We have a 300 by 100 matrix, which is 30,000 entries plus 100 for the bias. That's why we have that many parameters needed to go from that first to second hidden layer. And then finally, we're going to the output layer, which is 10 dimensional. Okay, if we add up all the parameters happening here, we have 266,000 parameters just for 2 layers. And these layers are narrower than our input, right? So that's crazy, right? Yeah, that really is when you think about how many parameters you have to train. Okay, so let's see how we would actually run this. We've specified our architecture. The next thing we need to do is specify our loss function. So we specify the loss function because this is a classification problem. We're going to use this cross entropy. And this here is important. From logits equals true, what does this mean? Basically, this is saying that we did not specify a softmax in the output. We could have, right? When we made our last layer, we could have put a softmax activation there, but we didn't. So because we didn't do that, we're telling, we're saying, you know, when you're calculating the loss function, just know we have not applied any softmax yet. What's being output from the network are logits, and those are not probabilities. Those can be on any kind of scale. And then it'll take that into account when it computes the loss. Okay, so, and then we can, you know, compile the model with, we'll just specify the optimization we want to use. Let's use Atom. And this is our loss function. And let's say we want to look at accuracy for our metric. Okay, and so this is actually going to train in a sequence of epochs. At each epoch, the code breaks the training batch into mini batches of size 50, and cycling through the mini batches, it trains the neural network. So let's try it. So now we're actually, you know, training the network. We're fitting the, we're fitting these network parameters to the training data. Here we've got 5 epochs. Okay, and so that, you know, I mean, it took like, I don't know, 20 seconds, but it didn't take that long to find 266,000 parameters, really. It's pretty impressive. And so you can see the accuracy, and again, this is going to be the accuracy on the training data, decreasing until it decreases to 0.989 in that final epoch. Okay. All right, and this is just kind of emphasizing what I said about the logits, because we didn't apply the softmax specifically in our architecture. The model output isn't constrained to be in the interval 0, 1, could be anything. And so these values are referred to as logits. They're not probabilities, they're logits. And that's what they're referred to in the TensorFlow documentation. And so to convert them to probabilities, we would need to apply a softmax. So let me just illustrate here with an example about what's going on. So let's say I look at one of my test data points. So I take a test data point and I apply the model, and I look at what is the neural network spitting out when I feed in this test point. So if I look at what it's spitting out when I feed in that test point, I get the following. Okay, so I've got like a minus 6 minus 1, 0.85. Okay, so these numbers are kind of all over the place. There's negative numbers, positive numbers, and they can be large, small, etc. And so I could also obtain this output by calling the model.predict function, and that would actually give me the same thing. So if I did model.predict of my test point, I once again just get this output of the neural network, which you see here. So if I want to convert that into a probability distribution, what I can do is I can take the output of the model and I can just apply the softmax function to it. So I take the model output, I apply the softmax function, and this is what I get. It probably takes a second to kind of parse that, but look at these numbers are really tiny, right? This is tiny, 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 tiny. Ooh, okay, this is my non-trivial entry, right? This is 0.9998. So that one's essentially 1, and the other ones are essentially 0. So this is really close to just kind of telling me where that maximum entry is. And where is that maximum entry? Well, it's corresponding to the 7s, right? These are my 9s, these are my 8s, these are my 7s, because this is that 10-digit classification problem. Okay, so that test point, the model thinks it's a 7. Okay, so let's see now if we apply it to all of the test data. So we can evaluate the model on the test data with this model.evaluate. And then just like before, we can look at a confusion matrix. Okay, so here, to actually compute a confusion matrix, that's not based on a probability distribution for each test point. So to do that, what are we doing? We're taking the prediction and then we're looking at the argmax. So here we're actually just doing the classification based on wherever the maximum value occurs. We're going to call that a 7, right? So in the above example, we would look at this data point and we would just call it a 7. And that's how it's computing this confusion matrix right here. Okay. But if we do that, so we take the model output and we just, take the category corresponding to the largest entry and call that our prediction, then we can compute this confusion matrix and we get an accuracy of 0.97, right? And that's really good for this data set, which is challenging. And we didn't use like a crazy large neural network. That was pretty good. Okay, and so you could have just added a softmax activation to the output layer. So we could have just done that from the beginning, and you might think that that would be just simpler, and it would be. But the documentation recommends that you don't do that for numerical stability reasons. So it's kind of like would be simpler just to, specify in that last layer a softmax activation for your output. And you can do that, but it's recommended that you not. If you do, you want to live wild and crazy and do it anyway, then just make sure that you don't specify logits as true when you do your loss function. So, right, which I'm not doing here. Right here, I just have this sparse categorical cross entropy, but I don't have the logits as true. Okay, so let's try this, and we should get very similar results because I've not really changed anything in the architecture. I'm using the same optimizer. So the only thing I'm doing here is having that softmax added to the last layer. Okay, and so we got 0.989. I really think that's kind of what we had before. And then this is the performance on the test data, 0.975. what did we have before? Maybe we didn't actually compute that number before. I thought we did. Oh, yeah, well, 0.97 there, accuracy. Okay, actually like a little bit higher.
Well, the accuracy on the training is about
Yeah.
for the other one too. So it's about the same.
It's about the same. I agree. It's about 99 on the training and about 97 on the test. But on this time, it was like maybe slightly better on the test data, with 0.975 instead of 0.97.
On mine was 0.978 on the last one.
Oh, yeah. So good point. These things are random, right? So just because it comes out slightly better once doesn't mean it's going to come out slightly better all of the time. So, because I don't think I've set a random seed here. So I think it's going to vary depending on your run. Yeah. So indeed, so be careful drawing conclusions from just one run of things, because you may get something different if you run it again. Like in this case, let's see what I get. 0.977. Okay. So one other thing that you can do is add something called a dropout layer. What a dropout layer is, okay, let me actually go back up to my initial picture. Okay. And okay, right. So what happens in a dense layer is that, I wish I had another hidden layer in this figure, but is that every neuron feeds into every other neuron. So if I'm here, this neuron's going to have a little arrow going to all of the neurons in the next layer. If you add a dropout layer, you randomly remove some of those arrows. So you randomly like take out some of those connections. So it's not the case now that everything is flowing into everything else. You have dropout where you randomly take out some of those arrows. You might think, why do you want to do that? A good question. Sometimes you get more robustness that way. I don't know that I have a great explanation as to why that's the case, but sometimes when you put in a dropout layer, it can help with the robustness of your network. And so that's what we're doing here. We're basically taking, we're flattening, and then we're doing this 2 dense layers, and then we're doing a dropout layer before we feed into the output. Okay, so let's try it with the dropout. That's the only thing that's changing. So here, right, because I don't have the softmax in my output layer, I have logits equals true in specifying my loss function. And once again, I'm using atom and 5 epochs. And let's see if I can do any better with dropout. It's hard to improve a lot from 99%. So, but actually, I think this is illustrating the point maybe well. Okay, my accuracy on the training data did not go up. Maybe it went down a little bit, but my accuracy on the test data set went up a little bit. Whether that's just random or whether that's going to be a consistent pattern, I'm not sure, but it is consistent with this idea that the dropout is helping with the robustness a bit and is helping with the generalizability to the test data. Okay. All right. Any questions on that before we talk about pre-trained networks? Yes.
So is the dropout layer like an actual layer with nodes, or is it just the process of dropping some arrows between 2 layers? Because we don't have to specify a number of nodes for it.
Right. So I think you shouldn't think about it as like, yeah, I don't think it's its own layer in the sense of having its own neurons, because you're exactly right. We didn't specify the size of that thing. So what I think it's doing is just, we had arrows going from that second hidden layer to the output layer, we had, all of the arrows. And now I think it's randomly removing 20% of them.
Okay.
Yeah. But yeah, that's a little confusing. But yeah, but it's kind of like this flattened layer. The flattened layer is not really doing, it's not, I don't know if you want to think of it as a layer exactly. It's just flattening the data, but everything's a layer. Other questions? Okay, so let's take a look. So the last thing we're going to talk a little bit about is how we can use a pre-trained network to do some pretty cool things. We already saw that even just this little network had 266,000 parameters. And to really do a good job on hard tasks, you're going to need a much larger network. These can be difficult and time-consuming to train. But once somebody does, sometimes you can take what they've already worked hard to train and maybe apply it to your own problems. So there are many examples of what are called pre-trained neural networks. You can check them out here. And these are very large, and they've been trained on giant computers using massive data sets. So not things that you could probably do on your laptop. And so these are basically, they can be useful in a couple of different contexts. One is as an initialization for a neural network. So you might take this pre-trained neural network and you might add a couple of your own layers on top, but you might use it as the starting point. You take this complicated network someone's already worked really hard to get good features out of, and then you add a couple layers to sort of adapt to your task, but you're building on that foundation, and that's called transfer learning. I mean, you could also just use it, right? If you have the same task, you can just use the network directly. But perhaps in a more interesting setting, you might want to take it and then add a few layers and adapt it to your situation, and that's called transfer learning. So let's take a look at a neural network which was pre-trained for image recognition. This one was trained on the ImageNet dataset, which I mentioned last time, as it contains about 14 million images belonging to 20,000 classes. So really huge data set and challenging because such a large number of classes. So if we want to access it, we import TensorFlow, NumPy, and then from tensorflow.keras.preprocessing, I'm going to import image. Okay, so that's referring specifically to that, like, okay, I think that's referring to the ImageNet. We're going to specify ImageNet there in a second. And from the TensorFlow Keras applications, I'm going to import VGG16, which is like a complicated architecture. Okay, so once I have those imported, I'm going to make my model, which is my VGG model, in the following way. Okay, so now that I've imported this thing, I can define my model to be the same as the VGG16 model. I'm just going to use the VGG16 model. And for my weights, I'm going to use ImageNet. Okay, so think of this VGG16 as specifying the whole model architecture, how many layers, what sizes, exactly everything that you're going to do. So that's really telling you the architecture that you're using. And then this part is saying, I'm going to use the weights, I'm going to use the W's that were obtained by training on the ImageNet data set, right? So you could do that same architecture with different weights depending on what data set you trained on. And here we're going to train on the ImageNet. We're not going to do it. They did it. We're just going to use it. Okay, and then you have an option here, include top equals true or false. So you can say, yes, I want to include the last 3 layers of the network, or you can say, no, I don't. I'm going to make my own. I'm going to start with this and I'm going to add my own layers. Here, we're just going to include the layers and look at exactly what's there. Okay, so here's the summary. So this is impressive, right? What are we inputting? We're inputting an image, and we're inputting an image which is 224 pixels by 224 pixels. Here, we're not going to flatten the image because generally neural networks for image processing want to utilize the underlying spatial structure there, right? They want to take the square, they want to, like run filters over the square. And so generally you don't want to make it a vector. You want to keep it as a square and process it that way. It's a little bit more complicated and we haven't talked about it, but just so you know, for image processing, normally you're keeping it as a square. That's why you see it here. And what is the shape that's going in? 224 pixels by 224 pixels by 3. Keep in mind, these are color images. So that's going to be like the RBG, values that are determining what the color is. So I don't know how familiar you are with how colors work on a computer, but a color is defined by, 3 numbers, which is the red, the green, and the blue. Okay, so that's what we're feeding in. And then we have a lot of convolutional layers. These are a little bit different than what we talked about, but they're really good for image processing. And then we have something that we haven't seen before, which is a max pooling layer. This is also helpful for image processing. And what you do in max pooling is you might take a little patch of pixels, maybe you have, here it looks like what you're doing is you take a little patch of 4 pixels and then you replace it with the maximum value, right? So out of those 4, what's the maximum value? Replace it with the maximum. So when you do a max pool, the size of that image is gonna get smaller, right? From 224 to 224, you go to 112 by 112, which is 1/4 of the size. So every time you do the max pool, the size gets a little smaller, but you're increasing that third dimension. Think of that as like the number of channels. You're increasing that. And so this is complicated. Let me not get too bogged down here, but it's a composition of convolutional layers and max pooling. Until finally at the very end, you flatten everything out into a long vector, apply a couple of dense layers, and then output your predictions. Okay, which looks here like it's 1,000 different categories. So this is, okay, it's not all of the categories in the whole ImageNet data set, but it's 1,000 of them. Total number of parameters here, 138 million, right? So that's a lot. Okay, so, but what's cool about this network is we can just use it, right? Without having to train it. So let me show you in the folder for today, if you look, let me find it. Okay, so if you look in the lectures folder, you may have noticed that there's a little folder of images. So inside images, we got different pictures. Oh, we've got cute little dogs. We've got Scout. Okay, so there's like different images in this folder. And so if we can specify one of these images by specifying the image path. Okay, this is where to find the image in the folder. Then we can load the image. And then here's just a little bit of processing to make it the right type of input to go into the network. But after a little bit of processing, we've loaded the image, we've done a little processing, we can just feed it straight into this VGG model and see what it predicts. So this is Scout 1. That was that second picture that I showed you. And you can see what it predicts. So it thinks it's a soft-coated Wheaten Terrier with probability 0.35. It's an Old English Sheepdog with probability 0.23. Wire-haired Fox Terrier with probability 0.13. These are very specific categories too, right? This is not just like dog or cat. This is soft-coated Wheaten Terrier. Okay, so highly specific. I think it's a soft-coated Wheaten Terrier. Does that look right? Anybody know about dogs? I actually don't quite know what that looks like, but I think that's probably correct. Okay, and this is of course just giving us the top 5 because we don't want to see the probabilities for 1,000 different categories. Okay, so that's pretty cool, and you can try it with your own pictures. So just whatever picture you want, throw it into the network and see what does it think it should be. What's the classification?
I think it is a soft-coated Wheaten Terrier.
Is it a soft-coated Wheaten Terrier?
I think so.
Okay. I mean, but that's a great illustration of how impressive some of these things are, right? It's highly specific, right? More specific than we probably would have been able to guess. Okay, so a couple topics that we didn't get time to discuss. Recurrent neural networks. I think I mentioned those briefly last time. Those are really good for time series. If you have time series or if you have any kind of sequential data, those are good for that. Let me see what I have in my chat. Soft-coated Wheaten Terrier. Yes, I think there's a consensus. Those can also be useful like for language processing, because you've got like that sequential order of the words there that's important. So RNNs can be useful for that. And we didn't have time to talk about how neural networks can be used for unsupervised learning problems and for reinforcement learning problems. We haven't talked about reinforcement learning at all. In that context, agents are trying to maximize some notion of cumulative reward, but there's applications to these areas as well. So this is a very broad area. And we also didn't look at basically doing implementing these things with like parallel, code implementation. So we're just running all of this on my laptop, but you can look at doing TensorFlow on a GPU where you parallelize things. We're not going to talk about that in this class, but there's good support for that if it's something that you want to do. Okay, well, it looks like I'm over time, so why don't I call it a day? And thanks everybody. There is an activity in the folder which we didn't get time to do, but if you need more activities, if you're looking for more activities to do to finish your 5, then that's one that you can do. And it'll be a fun one because you can like play with image classification. So if you're looking for more activities, see the one in there. Otherwise, have a great night, everybody. And yeah, see you guys on Thursday, or they will. Okay. Yeah.
Would you consider allowing us to do extra activities or like points back on assignments that we missed?
Extra activities to earn points on assignments. I would have to, I can bring it up with the rest of the teaching staff and see what the reaction is. I mean, to be honest, the activities aren't a big part of your grade as it is, but we're trying to do something to kind of encourage like live attendance and participation. I feel like we didn't do a great job of that because we tended to not save